In this submodule, we will discuss how to input parameters into programs to tweak their behavior and how a program can return results in a different way than print statements. As our focus in this section is not on the application writing, we start with the pre-made application. Our goal in this application is to measure the error rate of the measurements of entangled qubits. We do this by generating entangled qubits and then measuring them and sending these instructions to the QMPU. We do this 20 times and then we print our measurements. So in this application, we've combined both the receiving and creating side of the programs. We've done that by giving this program an internal variable, isCreate, and depending on this isCreate, we will either use the createKeep method or the receiveKeep method. And then we've also made the peer name configurable by setting this self.peer as an input argument. We provide these inputs over here at the initialization of the tutorial program class. So we provide the peer name and the isCreate. This allows us to create two separate programs. One, for example, for Alice, which is doing the creation, and one for Bob, which has the creation set to false and then does the receiving. We can also use this to change the hard-coded 20 iterations to a configurable number. And we do this by providing num APR pairs. We will put the default to 20 such that the previous behavior is preserved. And then over here we define new parameter num APR. And then we replace the hard-coded 20 with this new internal parameter. And this allows us to then configure the number of APR pairs we use as we wish. And then we can, for example, improve the statistics when we want. Now, let us run this application. So we see if we run this application, we get two lists. And in these lists, we see these future type objects. I think we can see the values of the future type objects, but this shows, again, one reason why it's good to convert these future type objects to integers once you're sort of done with the main body of the quantum program. So we'll do this by casting each future into an integer for m in measurements. And then if we run it again, we get a much cleaner looking two lists of measurements. So we can see already that there are some measurements which have different values. That's because we've configured the link model in this case to have a fidelity of 0.8. So there will be some measurements not matching. Since our goal of this application is to calculate the error rate, and we want to do that automatically, we don't want to manually look at these measurements. So in order to automatically calculate the error rate, we would have two options. The first option would be to use the classical messaging system to, for example, send the measurements from one node to another node. But the other option, the one which we will be using, is to send these measurements back into the run simulation file. And we can do that via returning the measurements. And we'll do that with a dictionary where we say we'll give this a key. You can choose that however you like, but I will call it measurements. And then we can provide the actual object that we want to send back, namely the measurements. So now we will move on to the run simulation PY file to look at the other side of this picture and then also finish this error rate calculation. So this run_simulation.py file is similar to the ones we've been using in the earlier submodules, but there are some differences. Namely, over here, instead of using an ls program class, we use the tutorial program, and then use that tutorial program to create an ls program instance. And then we configure this tutorial program with the peer name. So we set that the peer for ls will be Bob. And then we specify this is create to be true, so that ls will be using the create keep. And then Bob, on the other hand, he has as peer ls, and he will be using the receive keep method. So with this code, we can use the same tutorial program class for the program to create two different program instances that cooperate to form the entire application. We can also now add this new argument that we have created, namely the number of EPR pairs. So, for example, we can now increase it to, say, 100 to improve the statistics of our simulation. So, in order to get your results, you get them back from the run method when applicable. So we can take the results ls from here, and also results Bob. Now these results, they are structured, well, we have to discuss a little bit how these results are structured. So if I, for example, print the results of Alice, you will see that we will get first like a list and then the dictionary. It will become a little bit more clear if we, for example, first decrease this a little bit, and I can show you how the structure looks like. So here we have this list, and inside we have this one measurement. The reason why this outside list exists is because we also have this parameter, like the number of times, which specifies how often we want to run our simulation. So for example, if I increase this to, say, 5, then we will also get 5 different returns from this. For now, we will just leave this to 1, and we will put all of our simulation efforts into just creating more EPR pairs in a single simulation run. But in order for us to get back just this list of measurement results, we will need to do 2 things. Namely, we will first need to pick out the first element out of the list, and then we take this key measurements out of here. And then we get back the list, and we'll do something similar for Bob. Now, we can quickly verify it. If we now print the results of Alice, we get just the list of measurements. So using this, we will complete our section where we will calculate the error percentage in these qubit measurements. So we will calculate the amount of errors, and we will do that by result Alice is not equal to the result Bob, or result Alice or result Bob in zip results Bob. And then we have to, now we just have a list of the errors, and we will calculate our error percentage by first summing the errors, then dividing by the length of the errors, and multiplying it with 100 to make it a percentage. And then we will print now we can run this code, and we get back our error percentage. That concludes this submodule on program input and output. I will see you back in this next submodule, where we will conclude our module, and I will show you how we can do a sweep over a parameter in the network configuration, and we will use this to generate a plot where we show the error percentage versus this parameter of the network.